Yeah, so welcome everybody to the International Seminar on Automorphic Forms. Today we have Romain Branchereau from the McGill University that will teach us about the Kudla-Millson lift on the symmetric space of SLN.
Thank you for the introduction and for having me today. So yes, today I want to talk about the lift on the symmetric space of SLN. So I'm interested in quotient of that form, so we call it S gamma. It's a double quotient of SLN R mod SON and modulo gamma on the left, where gamma is some torsion-free subgroup of SLN Z. And so the goal is to construct a lift that I'll call E phi that goes from the n-1 homology of S gamma to the space of modular forms of weight n for some gamma prime in SL2Z. And that has a property that, so if I evaluate at a Z in the Hn-1, this modular form has a nice Fourier expansion of the following form. So the Fourier coefficients are intersection numbers between the cycle Z, that's the input, and a certain family of special cycles of codimension n-1 in S gamma. And the pairing, so this pairing here is the intersection pairing between the n-1 homology and the complementary, so the complementary dimension is n squared minus n over 2. Relative homology. So I want to construct a lift, a map like that. And so as if you're familiar with the Kudla-Millson lift, you see that this is completely analogous to the construction of Kudla and Millson. So Kudla-Millson in the 90s, they constructed a similar lift with the same property that the Fourier coefficients have a description in terms of intersection numbers of special cycles. So that was for the similar construction for locally symmetric spaces of orthogonal groups of signature PQ. So the goal is to transpose their construction in this new setting of SLM. Okay, and so the two will also be related. So if you're familiar with the theta corresponds and the dual pairs and the seesaws between dual pairs, so there is a seesaw relating with the construction I want to present today and the Kudla-Millson lift. So the underlying seesaw is when you take signature PQ is NN. So you have the pair SL2 SONN for the Kudla-Millson lift. And then you can embed GLN in SONN diagonally. So you have this other pair GLN, GL2, and this is essentially the seesaw that kind of relates the two. And then there is another relevant construction. It's so more recent. It's the work of Bergeron, Charolois, Garcia. It's recently, 2019 maybe. So they also constructed a lift that has, call it EBCG, that also takes as input the n-1 homology of this locally symmetric space of SLN. And it also gives a modular form of weight n and some level gamma prime. And so it's also an attempt to kind of relate their construction with the Kudla-Millson construction. So it's not completely clear from the construction I do. It's very likely that the two lifts are the same, but it's not. It doesn't follow directly from the computation I do. And so the main difference between also their construction and what I'm discussing today is that this lift, they don't have the geometric interpretation of the Fourier coefficient. So this is also the new addition in this construction I'm presenting today. So no geometric. Okay. Okay, so the question which is not completely clear is the lift that are the two lifts the same? And it's probably yes, but not completely conclusive from. For n equal 2, it is can deduce it, but in general, it's not completely clear. Okay, so this is essentially the idea is to discuss such a lift. So the first step is to I have to tell you what are these special cycles, so that we will have in the Fourier expansion. So so first, before considering the space of SLN, we need to consider the space of GLN. So that's the space X of positive definite symmetric matrices of size n by n. Okay, so we can act on the space by GLN, or the connected component of a GLN of matrices with positive determinant. We can act on X by taking a matrix and acting by G, ZG transpose. And the stabilizer is SON. So we can identify X with GLN GLN R mod SON. So that is of dimension n square plus n over 2. Okay, and then inside of that we have the space S. So S is all the matrices of determinant 1. And that is SLN R mod SON. And that's of dimension n squared plus n over 2 minus 1. Okay. So as I said, like in all this construction, so it's the space SLN, but there is the underlying quadratic space. So that's reflected in this embedding in the seesaw that I wrote in the beginning. So there is talk about GLN and SON, but there is an SONN in the background. So there is an underlying quadratic space. Of signature NN, so that's Rn with the quadratic form Q, so QV so the underlined V will always be an element. It's a pair of two vectors in Rn. This quadratic form of signature NN. And so we have presentation of GLNR in SONN, so it acts on the first component by G, and on the second, the V2, it acts by G inverse transpose. Okay, so okay, so now for each V in Rn cross Rn, for each pair of vectors in Rn, we can define xv to be all the symmetric matrices in X, for which Z, so it's ZV2 is equal to V1. So that's a submanifold of X of codimension N. Okay, maybe why this the submanifold. So if you know about the Kudla-Millson construction, so in the Kudla-Millson construction, you can consider locally the symmetric space D. That's SONN by SON cross SON. And then inside of that, you have the D, some similar submanifolds, DV. And then the XV is the intersection of the X embedded in D with DV. So XV is X intersected with DV. Yeah. So from this embedding here, from this representation here, you get this embedding here. Okay. So this is for the space X, and now to pass to something on the space S, we take the projection. So we have projection from X to S that takes a symmetric matrix, and so you divide it by the determinant. So Z1 is Z. So we have this projection. The fiber is a positive real number, so we can see X as a fiber bundle over S, and we can also, if we compose, like if you use the exponential, you can see it as a vector bundle of rank 1 over S. So X is S cross the positive real line. And so then SV is the projection of this XV inside S. So this had codimension, so XV had codimension N in X, and then the projection will have codimension N minus 1 in S. Okay. Okay, let me give you two examples or two special cases. So the first special case is if you take V to be the pair of two basis vectors. So let's take V is E1, E1. Then XV, it's all the matrices which Z E1 is E1. So we get all the matrices of the form 1, 0, 0, Z prime, where Z prime is in the smaller symmetric space GLN minus 1 mod SON. Okay, so we see that this submanifold is the image of a smaller copy of the symmetric space embedded in the larger copy, the symmetric space. So we also have, yeah, I didn't mention, so we have also the following invariance properties. So if you know the Kudla-Millson cycles, we have the same property. So if you act by an element G and G ln R on the cycle X, on the submanifold XV, has the following. Sorry, I call this rho, so rho G of V. That's for all G's and G ln R, so that we can always reduce to the case where XV is for V is a pair of two basis vectors. And so we can show that in general, the XV is always, after translating, it's always the image of a copy of GLN minus 1 mod SON. And when you restrict the projection to XV, it's a diffeomorphism. So really the SV, they're all copies of the symmetric space here inside of S. So maybe let me now write down an even more concrete example. If n is equal to 2, then X is GL2R mod SO2, that's H cross positive R, and then so S is the upper half plane. Now suppose I have V, that's a pair of two vectors. Let's call the coordinates P1, P2 for the first vector, and the second Q1, Q2. Then XV is the geodesic with endpoints. So the first one is Q2 divided by Q1 and minus P1 divided by P2. Oh, sorry, that's SV. Okay, so it has codimension n minus 1, which is 1, codimension 1. Okay, so the next step is to, so we have the submanifolds. The next step is to pass this to the quotient. So we need to introduce some lattices. So let's take some lattice L in Zn, and then we consider, so L, curly L is L cross L. And then the dual of that it's so it's the dual with respect to this quadratic form on Rn cross Rn. Okay, so we call Q of V. V was 2V1, V2. Okay, then we can look at the discriminant L dual mod L and can fix a test function. So we can think of what I'm going to do is I produce a scalar valued modular form. So this chi, you can see it as like a Schwarz function, a finite Schwarz function. You can also do the same construction in terms of vector valued modular forms, and then you don't have to add this chi. So I add this this test function to produce a scalar valued modular form. And so it's just a linear combination of translates of the lattice L. Okay, so we can also view chi in here. And then let's take gamma in SL and Z that is torsion free and that preserves preserving chi, so in the sense that it preserved by the veil representation, which is here the action. So we want that. Yeah, preserves by the action of rho gamma for all gamma. Okay, then we have so the projection from X to S passes to the quotient. So let's call X gamma X mod gamma, and then S gamma is S mod gamma. And the projection passes to the quotient, and then we define, so ZV so recall we have the SV is in here, and then the ZV is going to be the quotient by gamma, and that's now in S gamma. Okay, and I should also say it only depends on the class of V in on the class of on the class of V mod gamma, because we have the invariance. We have the following invariance. Okay, and so here gamma acts on V by rho. Okay, so we have the cycles, and then we can form a special cycle. That's the linear combination of the cycle weighted by this test function. Okay, so we take the sum over all vectors of, so we need that so QV is equal to 2n. Okay, and so now what we have is, so we have a cycle of codimension n-1, so that's dimension n squared minus n over 2, and S gamma relative to a boundary. Okay, so if we go back to the example where n is equal to 2, then we can pick the following lattices. So let's take L to be just PZ4. So P in the two components, we just take PZ squared. PZ squared. So the dual is P minus 1 Z squared. P minus 1 Z squared. And then the characteristic, so we take chi to be the characteristic function of the following. So the first component, we take it to be coprime to P, Second one is divisible by P, and the last two just Z squared. Okay, and with these choices, so the gamma is, so that's preserved by gamma 0p. And so S gamma is the modular curve Y0p. And then, so I told you that each ZV is like a closed geodesic. And so then the Zn chi will be a finite linear combination of, oh yeah, I didn't say this. This is a finite sum. So it's a finite sum. And then, so in this setting, this Zn chi, so this linear combination of geodesic, is the nth Hecke translate of the geodesic that goes from 0 to infinity. Okay, so these are the cycles. So the next step is to construct this theta kernel that will have these special cycles as Fourier coefficients. So I'm not going to go too much into details now. Maybe at the end I will say a little bit more about the construction of the differential form. But so the idea is that you have some work of Mattei and Quillen that produces certain Thom forms for vector bundles that you can use to construct a form phi z v in two variables z and v. In the first variable z, it's an n differential form, a differential n form on x, and in the second variable, it's a Schwarz function on Rn cross Rn. And so it has the properties that it is closed. It has the GLNR invariance that if you pull back by G, you can, it's the same as acting by rho on V. And it has this geometric property that is crucial to get these Fourier coefficients description in terms of intersection numbers, that is, it is a Thom form. So it's a Thom form for XV. Okay, so for now we have a form on X. So we want, in the end, we want a form on S, but for now we have a form on X. We can build the theta series. So it's theta phi. Okay, it should also depend on chi, theta phi chi of z tau. That you get by applying the Weyl representation and summing over the lattice curly L. And then what you get is it's an n form on X and a smooth function on H that transforms like a modular form of weight n. And that is holomorphic in cohomology. So if you apply d bar, it's not going to be 0, but you can construct a transgression form so that more like theta, it's also a theta series, so that if you look in cohomology, it's holomorphic. And then to get a form on S, so we use the projection we have this projection map, takes Z to Z1. And then the form that we get, that we define, is E pi chi of Z1 tau. And I add a complex parameter S is the push forward along this projection. Okay, and what is the push forward? So if you have the push forward of, so on X, you have the coordinates Z. So Z has coordinates, I can write in coordinates Z1 and U. So you can write each form, different form in the form eta 0 plus eta 1 du over U. And then the push forward is the integral d1 du over U. So that's why we integrate basically over the U variable. So what is left is the Z1 variable. And so this is now it's now an n-1 form on S. And yeah, I also didn't say, so this, here it's, the theta phi is an n form on X, but it's also by the invariance property that I wrote down, it's gamma invariant. So this one will also be gamma invariant. And it will also transform at S equals 0 like a modular form, and it will also be holomorphic and in cohomology. So that's the first theorem. So it converges for any S in C. So the S I added because when you want to bring the 0 infinity inside of the sum, then you need to take the real part of S greater than 0. And that's when you will have an expression in terms of an Eisenstein series. But if you keep the 0 infinity outside, it converges for any S. And then at S equals 0, so E phi chi is a closed, so a closed form on S gamma, so n-1 form on gamma, and so it defines a lift. By integrating over the cycle Z. So if we take a cycle here, because it's closed, it only depends on the homology class. And then in the second variable tau, in the variable tau, it transforms like a modular form of weight n, and it will also be holomorphic, essentially by the same, because of that. So you have to, yeah, use this fact to show that it's a holomorphic modular form that you get. And it has the a description, so the Fourier expansion that I wrote down in the beginning. In terms of these special cycles, and this follows from essentially this Thom form property of the differential form. And so so that's essentially this construction. And then when the real part is greater than 0, we can bring the integral inside of the sum, and we can apply a Poisson summation, and then we get Eisenstein series. So you can in general, for this n-1 form, you can just compute what this form is, and you see it has the form of an Eisenstein series. But let me show you instead what you get when you evaluate it on tori. To see that you get some Eisenstein series. So that's 3 evaluation on tori. So okay, so let's take F, totally real field of degree n, and let's fix the Z basis of O, the ring of integers. We can take that as the lattice L, and then we look at O cross O in Rn cross Rn. And then we can define, so by restriction of scalars, we get cycles, let's call it ZO, that's O so the totally positive elements of norm 1 in the field, we quotient by this totally positive units in O, and that gives a cycle that represents n-1 an n-1 class in S gamma. And if you integrate, so if you evaluate this class E phi chi over this torus, then you get up to a constant of pi's and gamma functions and something. You get an Eisenstein series, O cross O mod O1 plus 1 tau plus 2. You get this Eisenstein series at S is equal to 0, and that's the diagonal restriction. So here tau is, so this is tau in H, but this is the diagonal restriction of an Eisenstein series, a Hilbert Eisenstein series of parallel weight 1. Hilbert Eisenstein series. Okay, and this is also what you get when you evaluate the BCG lift on this. When you evaluate the Bergeron-Charlois-Garcia lift on these cycles, that's also what you get. So that's why it's follows that the 2 lifts agree at least on this tori, but it's not, I don't think it implies in general. So for n equal 2, it implies that the 2 are equal because you can get all homology classes by these cycles, but I don't know, I don't think it's true for greater than n, or at least if it's true, then it would show that the 2 are equal, but in general, I don't think so. So that's for these compact tori, and then you can also evaluate over split tori. And then instead of having the diagonal restriction of 1 Hilbert Eisenstein series, you get the product of n weight 1 Eisenstein series. N weight 1 Eisenstein series for SL2Z, the elliptic modular form. Okay, so the next is, next I want to talk about one consequence of this lift, which is also completely inspired from what Kudla-Millson did. So it's transposing, so what they deduce from their lift in terms of the spans of these special cycles, we can get the same result for these special cycles in SLN. So what we have constructed is a map E phi chi that goes from the n-1 homology modular forms. But you can, so instead of taking this theta kernel and integrating it over a cycle, you can also integrate it, pair it against cusp form, and get an adjoint lift okay, that's by pairing a cusp form against this E phi chi. And so we have a pairing between the Hn-1 S gamma and the Hn square minus n over 2. So the complementary dimension is so we have this intersection pairing here. Okay, and so one corollary from this construction is that the kernel of E phi chi. So the kernel of E phi chi lives here. So it lives here. And on the other hand, the special cycles, they live here. So the orthogonal complement of the span of the special cycles live here. So we can compare it with the kernel. And that's the same. So the span we take the span and then the orthogonal complement is the same as the kernel. And then when n is equal, when n is greater than 2, we get that the image so the image lands in here, and this is also by Poincaré duality the same as here. So we can we get that the image of this lift is the same as the span of the Z and chi. Okay, so here, yeah, you need Poincaré duality. Okay, and the case, the condition n greater than 2 is because you need to pair against some Peterson forms. So for convergence, take n greater than 2, but I think by regularizing, I think even Kudla-Millson also consider the case n equal 2, but it's because of these Poincaré series. Okay, so that's one corollary of this lift. And then finally, let me go back to the case where n is equal to 2. So let's fix P prime and recall that we have fixed, we can find this test function chi such that we have S gamma is the modular curve, Y0P, and the Z and chi are the n Hecke translates of 0 infinity. So yeah, so in that special case, what I get is that the integral of E phi chi over a cycle is the intersection number between Z and the nth Hecke translate of 0 infinity, and that is a modular form of weight 2 and level gamma 0p. So the lift, yeah. the lift goes from the H1 of Y0P to weight 2 modular forms level gamma 0P. Then let's fix a basis of this space weight 2 modular forms. So fix the basis of normalized eigenforms. And let's set the standard notation. Omega f is the one form, f tau d tau. And then omega f plus or minus is omega f plus or minus omega f bar. Okay, and then we can describe this, so the image of this lift in terms of these basis forms. We get the following. So E phi of z, so that's now a modular form of weight 2 and level gamma 0p. So we can write it in this basis, E to P and alpha, so alpha E is given by 1/2 I pi P minus 1. And alpha I is the L function of fi at 1, so normalized by some suitable period that it's an algebraic number. So that's the algebraic L function times the integral of omega f I minus over z. Oh, I forgot, here's the integral of okay, so we can write in terms of these bases, and we can, so it implies two things. So it implies, so first the lift is Hecke equivariant. So E phi chi of Tn z, Tn z is Tn when n and p are coprime, otherwise it's the adjoint that you have outside. So when they're coprime, they're the same, but otherwise it's the adjoint. And it also implies that, so the image of this lift, so we see we only get the forms fi for which the L function is non-zero. We can get that that's exactly the image. So the image is the space, let's call it M2 gamma 0p 0. That's spanned by the Eisenstein series, and then spanned by all the forms that have non-vanishing L function. Yeah, and also one last thing that we can deduce from that is, as I said, so if you integrate over, so you can generate the homology of Y0p by hyperbolic elements. And if you integrate over the cycle z gamma z of a hyperbolic element, that's this period over closed geodesics attached to totally real field that I have explained. I've told you that it's a diagonal restriction of an Eisenstein series. So combining the two results, we see that the space M2 gamma 0p 0 is spanned by diagonal restriction of Eisenstein series. So H1 0p spanned span Z0 okay, and so that's a diagonal restriction of the Hilbert-Eisenstein series. And so we deduce that M2 gamma 0p0 spanned by diagonal restrictions. Of Hilbert-Eisenstein series. And this is not a new result. So this was already proved by Yin-Kung Lee, a more precise result by a specific family of Hilbert-Eisenstein series. So this is more like to show that this lift can also recover this result. And I think so Lee's result more precise. Yin-Kung Lee, I think that was partially answering a conjecture of Yang about the general span of diagonal restrictions. And I also think that the same idea can show that, so there is another similar results of Borisov Gunnels that essentially the space M2 gamma 0p0 is spanned by essentially products of weight 1 Eisenstein series. And I think with some extra work, this could also follow from this lift, because if you evaluate on modular symbols, you get to product of weight 1, a sum of products of 2 weight 1 Eisenstein series. But on the other hand, you also get, you also land in this space here, so that's, you should get that it's spanned by these product of weight 1 Eisenstein series. But just one has to work a bit with the conversions, because you can't integrate on all the modular symbols. So you would have to avoid some of the modular symbols but I think with these some extra work, this could work. Okay, I think it's good time to stop. Thank you for your attention.